In the last class, we discussed regarding the IS code procedure for designing of foundation for reciprocating machines. All right. So obviously, the necessary data that is required, first of all, regarding the machine. So what is the detailed loading diagram? All right. So the loading conditions, then the plan, elevation, all right, section, and all those data, obviously. Apart from that, we need first of all the mass of the machine. What is the weight? What is the weight of the machine? Then of course the dynamic forces. Alright, what is the dynamic forces? When the machine will be operated, what will be the dynamic forces which will be induced? Then obviously, if there is any eccentricity, alright, so dynamic forces means the frequency, the amplitude, okay, operating speed, capacity, and exciting force, basically. All right, so that is the machine data that is regarding the machine that is required. Then again, regarding the subsoil, we have discussed that obviously the soil profile, subsoil profile. So what type of soil it is, what is the stiffness, what is the shear strength parameters. Okay, so that is the subsoil profile. So the soil characteristics, basically. Now apart from that, the other things that we require is the dynamic properties of the soil. Okay, the dynamic properties of the soil. So we will see one example today. So how to assess the dynamic soil properties for use in the machine foundation design. Okay, so these are the data that is required regarding the machine and regarding the subsoil profile. So dimensional criteria, as we have already discussed, so we need the area, the base of the block foundation. All right, so depth of the foundation, what is the depth of the foundation? So what is the depth of the foundation? All right, so greater the depth, greater its stability against rotation. All right, so it will prevent rotation, so it will hold the soil, hold the foundation from both sides. So greater is the depth, greater is the stability towards the rotation of the foundation. Then apart from that, we need to assess the center of gravity of the foundation system. So on not only the center of gravity of the foundation, but the combined foundation plus the machine. So this is a very important aspect for design of machine foundation. Alright, so if there is any eccentricity, we have to find out. So if the loading direction or the loading point is away from the center of gravity of the foundation, alright, so there will be eccentricity, center of gravity of the base area, so there will be some eccentricity. So if it is here, so there will be some eccentricity. So what will be the effect of that eccentricity? Alright, so there will be moments, destabilizing moments, so we have to assess that. Alright, so we need to check that. Obviously, apart from that, we need to check the vibration criteria. So we have already discussed that. So if we plot, so we see that, so the magnitude of displacement, it increases for the frequency factor omega by omega n, and this is the magnification factor. So as far as possible, we have to stay away from this position. So that is the basic meaning of the vibration criteria. So basically it is given there, so we have to be less than 0.5 and greater than 2. if possible. Then obviously the permissible amplitude. So that we have already discussed in the previous classes. And the permissible stresses. So we have discussed as in concrete, there will be steel, okay, then there will be wood, then there will be the vibration, I mean absorbing materials. So all the materials whatever are used in the foundation, so it has to be kept in mind that the permissible stresses in this materials, they do not exceed what is specified. Okay, for concrete definitely we can look into the IS 456. Okay, so apart from that, definitely the permissible stresses in the foundation soil. Alright, so in the foundation soil, so that has to be within limit. So that is one important criteria. So we can look into IS 1904. Alright, so for looking into that aspect. So the permissible stresses has to be within a limit. So for soil, we have the static cases. So we have the static cases for soil. So static case, that is a general foundation criteria. Against shear failure and against settlement, it has to be okay. And obviously against the dynamic load. So we have these other cases that needs to be satisfied. Obviously, we have seen that the center of gravity of the machine and foundation system. So that is an important. So positioning the foundation area so as to minimize the eccentricity. So that should be our primary focus. Okay, and then obviously determining the soil pressures which we have already discussed here. Okay. So how to design that? So what are the steps for designing the machine foundation? So first of all, we have already seen what are the design values of the exciting loads. So though these will be provided by the manufacturer. Alright, so this will be provided by the machine manufacturer. So what are the exciting loads? Then we have to find out the possible forms of modes of vibration, foundation vibration. Alright, so we have already discussed. So there are 6 degrees of freedom, 6 degrees of freedom. Then we saw that there are, I mean, for our particular analysis, we considered 4 modes of vibration. So out of that, 2 modes are independent. So about z-axis, translation about z-axis, and rotation about z-axis. So that is independent. Apart from that, we have 2 modes, which is translation about y-axis and rotation about this translation about x-axis, sorry, and rotation about the y-axis. So these two are coupled. Or alternatively, we can say translation about the y-axis and we have rotation about the x-axis. So ultimately both of these two modes are same and they are coupled. Alright, so if there is rotation about x-axis, there will be some amount of translation about the y-axis. Similarly, if there is translation about the y-axis, there will be some amount of rotation about the x-axis. So we have to determine these geometrical properties. Okay, the axis of rotational motion, CG of the whole system, that is machine and foundation, and moment of inertia of the base area. So the moment of inertia of the base area we can easily find out. So if the base area is rectangular, so we have to find out the moment of inertia about the y-axis passing through the center of gravity of the base foundation. Alright, so we have suppose this is the foundation. then this is the base area. So this is the base area. So this is what we are considering here. So obviously it is very easy. So if this is, suppose we write B, and if suppose this we write H, okay, so we have BH cube by 12, sorry, cube, okay, BH cube by 12. So this is IYY. So that is C. Okay, again, so this is about this axis. So this is required when we have to find out the forces due to non-uniform compression. So C phi I, so this I into R phi, that is the angle of rotation. So this I is this moment of inertia about this axis. Okay, so rotation is occurring about this axis, that is. Okay, so apart from that, we have to determine what is the polar moment of inertia about the CG, about the z-axis. So if there is a z-axis passing through in this manner, okay, passing through the CG, and if there is rotation about the z-axis, so that is required when there is non-uniform shear. So when there will be rotation about uh, this plane, okay, so about this plane, so this plane will move in this direction and then this direction, that is yawing motion, the yawing motion which we described. So in that case we need to find out what is the area, this polar moment of inertia. Okay, so in that case it will be sorry, so in that case it will be, we can write here, so we can write J theta, suppose if this is theta, alright, so J theta we can write, so that will be B H by 12, alright, so B H, so this is H, this is H, BH by 12 into B square by plus H square. Okay, so this is the polar moment of inertia about this axis, z axis, passing to the CG of the area. So polar moment of base area. Then moment of area of the base area about this axis we have already discussed. Okay, then mass moment of inertia. So mass moment of inertia we have to define for two axes. So one is obviously passing through the axis here. So if this is the center, and this is the axis passing. Okay, so we have the mass moment of inertia about this axis. So about that axis we can say M is equal to, we can say 1 by 12 M into, if this is H, suppose, and if this is D, right? So in that case we have H square plus D square. Okay, so this is the moment of inertia about the axis passing through the center of gravity of the mass of the foundation. Now, apart from that, we also require the moment of inertia about this axis, which is at a distance of L. Alright, and if you remember in the previous classes, we discussed that when there is a pitching and sliding motion, so the rotation occurs about this. So this is the moment of inertia about the O point. Okay, so that we can define as easily as, so m so mm is equal to m naught minus ml square. Okay, so we can find out. So this is the mass moment of inertia about the two axes, then polar moment of the base axis. Of course, uh, this is what I have told is very simplified case. So these are all simplified case. As we will see in the this following example, it is not that easy. I mean, not that easy means it is easy to find out the moments of inertia and the polar moments and the mass moment of inertia. It is easy. Okay, so it is easy, but the thing is that it is very tedious. Okay, so when the foundation is complicated, so suppose there is like this a foundation block standing here, then there is another block here. Okay, then there is another block on the other side. Okay, so generally the machine foundations are of this kind of block nature. Okay, so we have to again find out what the CGs of each block, CG of the base, alright, and then we have to add it up. Okay, and then so that is why it becomes a little bit tedious. Thing is that it is not very difficult, it is easy. The concept is easy, but calculating process is a little bit tedious, it is long. That is the main issue. So, yeah, apart from that, we have to compute the natural frequencies of the system. So, one is the motion about the z-axis, number one. So, that is omega n z is equal to root over CUA by m. So that is the frequency of motion about the z-axis. Then frequency of motion about the x-axis. Okay, number two. So about the x-axis we have, so this is translation omega n t z, omega n t in x direction. We have root over c tau a. So this is cu is coefficient of elastic compression, uniform elastic compression. So this is Cu. Then we have C tau, which is coefficient for uniform elastic shear. This deformation, shear, elastic shear. All right. So that is C tau A by m again. So we have two translational motion. Then apart from that, we have two rotational motion. So one we have number 3, that is, so one we have, so rotation about the y-axis. Okay, so this rocking motion. So for that we have omega n, so this is suppose phi. Okay, so we have omega n phi. So rotation about this axis, so we saw that this is the rotation, so we have phi rotation. So omega n phi in that case will be, we have C phi into I. Okay, I is the area moment of inertia of the base foundation. So just now we have defined about the axis of rotation passing to the CG of the base of the foundation. Alright, so this is the CG of the base of the foundation. This is the base of the foundation. Okay, and this is the point O which we have defined. So above that it rotates, so there is rotational motion. So for that we have the angular acceleration, and this is c phi I by mass moment of inertia about that axis. So mass moment of inertia about that axis, about the axis of rotation. So this is the angular frequency for this motion. Then we have the angular frequency about the z-axis. So if this is the foundation and this is the z-axis, so there is a rotation about the z-axis. Okay, so that we define as omega n, that is psi we can say, alright. So that will be C psi. This is for non-uniform shear, coefficient of non-elastic non-uniform shear, and the polar moment of inertia. Alright, so polar moment of inertia about this axis of this area, that is, okay, of this area, not of the mass, that you remember. So J, suppose J, alright, or we can write theta. So that is polar moment of inertia of this base foundation area. Alright, base foundation area about this axis, about the z axis. Okay, so that you have to remember about this axis. Okay, and on top there is the foundation. So that divided by, so mass moment of inertia about the z axis. Alright, so now we have to define the mass moment of inertia about the z axis. That is here. So these are the angular frequencies. Apart from that, we have to define what is the maximum amplitude. Alright, so a maximum amplitude of motion. So that is also we have to define. So first of all, in the z direction again, so number one, in the z direction we have, so z amplitude, we saw that we had pz by m into omega n tz square. Alright, so just now we have defined this term, and minus omega square. So omega square, here omega is the frequency of operation of the machine. So frequency of the loading, actually load condition, that is, alright. So frequency of the dynamic load we can see. So similarly we will have x a. So similarly we will have xa, so that will be px by m into omega n tx square minus omega square. Okay, then we will have the rotation about the z axis. The rotation about the z axis. So in that case, so we can say psi max. Okay, so that will be moment of inertia about the z axis by applied moment. Alright, so applied moment about the z axis. So this is applied moment about the z axis. So mz is the applied moment about the z, maximum, magnitude of the moment applied about the z axis. So mz, again we have the mass moment of inertia about the z-axis into omega n psi square minus omega square. Okay, and apart from that we will have for the combined motion, all right, for the coupled motion we will have two amplitudes. So one is x a, okay, so that is the due to the coupled motion, so that is the sliding in the x direction, okay, or the displacement in the x direction, maximum displacement amplitude in the x direction due to the coupled motion, so rotation and sliding. So in that case, so we have maximum displacement amplitude in the x direction given by we have already derived this, all right, so you just look into the previous slides. So al square plus c phi I, all right, minus wl minus square whole into px plus c tau al into my. So my is applied in about the y-axis, alright, moment about y-axis, and px is the force about the x-axis. So divided by, so we define a term delta omega square. And what is delta omega square? So delta omega square is mass into mass moment of inertia into omega n1 minus operating frequency of the system into omega n2 minus operating frequency of the system. Okay, so if you remember in the next last class we defined so that this particular system, so it has two modes of vibration and therefore two natural frequencies. One is omega n1, so we have a quadratic equation. So if we solve that quadratic equation we will have two values, so we will have omega n2, so we will have two natural frequencies. So this is omega one natural frequency and this is the other natural frequency. Okay, so we defined that in the previous class. So how to find that out? So that is delta omega square. Okay, so apart from that we have the phi a as well. Okay, so this is the displacement in the x direction. So this is the displacement in the x direction. So x a due to the coupled motion. Okay, coupled means sliding in the x direction, coupled with rotation about the y axis. So this is the maximum amplitude. Apart from that we have the maximum rotation, capital phi amplitude, which is equal to c tau a l into p x plus c tau a minus m omega square into the applied moment about the y-axis divided by delta omega square. Okay, so these are the terms we need to find out, and obviously all of them have to be within the permissible limits. All of them has to be within the permissible limits. So that we have to be, I mean, that is basically the design of foundation. Okay, so this part is easy. So we obtain the natural frequencies in translation and t x and phi and omega and psi. So these are the natural frequencies. Similarly, we have the uh, amplitude of motion. So Z amplitude, XA. So XA in this coupled motion will definitely be more. So we can consider that one. Alright, and then the maximum angular rotation about either y-axis or x-axis. So this 6 parameters has to be within the permissible limits. Now, how to determine the soil parameters? Okay, how to determine the soil parameters? So there is a very good example given in the book by Shamsher Prakash, which I have already shared with you. So in the book by Shamsher Prakash, you can look into the example. So example 9.1. Okay, so example 9.1. So you can look into that. So what it gives is, first of all, it gives the soil profile. So we can see that it is mostly sandy, all right, clay, sandy clay and clay sand. Mostly sandy clay, all right, of very low plasticity. All right, so we can see here. So the plasticity, this is liquid limit, and this is plastic limit, and this is the water content. So in between this, all right. So this is SC soil, all right, sandy clay, all right. So similarly, we have SM and SC, all right. So clay of sandy clay of very low plasticity, and along with that, we also have some amount of clay. So we have this properties given. So this is the subsoil profile. Of course, apart from that, we have the N values. So it is beyond this, we can say, all right. So in this range, so it is almost SPT N value is almost 20. So we can say that it is significantly stiff. The soil is stiff. So in fact, we can say from here itself. So if it is more than 10, so it is almost on the stiffer side. Okay. So that is the soil profile. Apart from that, there are other data. So now from here, what are the things that we can obtain? First of all is the what? No reply. First of all is the okay, bearing capacity. So if you remember, there are various options to use SPT N values to directly use the SPT N values, and we can find out what is the maximum, safe bearing capacity, all right, or ultimate bearing capacity. So there is the Tanks formula, all right, Tanks correlation. Then there is the Meyerhoff's correlation. All right, then there is Terzaghi and Peg correlation. Okay, so directly from SPT N value we can get the this one. So we can average it out to the twice B. So twice B we average it out, whatever is the SPT N value we can average it out, and we can take that value and we can find out the SPT N values. Apart from that, we can also find out the settlement. Okay, so what will be the settlement in this case? We can also correlate the SPT N value to the elasticity modulus, because here the type of soil is already given. So for that type of soil there are correlations, various correlations correlating SPT N value to the elasticity modulus of the soil. Okay, then we can correlate that to the velocity, shear wave velocity. Okay, so that various correlations are there in the literature. So we can find out for the static case, what is the allowable bearing pressure of the soil. So limiting the the permissible settlement, and considering the shear failure criteria, so we can find out what is the allowable bearing capacity of the or bearing pressure of the soil. So that is obviously not under our scope of discussion. I hope you have already discussed that in the foundation geomechanics or foundation. This design of foundation class. Okay, so that is that. Apart from that, so this is the data, subsoil profile data. So apart from that, what is given is the cyclic plate load test data. Okay, so we see here it was loaded up to this point and then released. Then again loaded up to this point and released. Then loaded up to this point and released. So we know, we have discussed as in cyclic plate load test, that in cyclic plate load test, so if we consider this one, so we have a total deformation. So this is the total deformation. Okay, so this is the total deformation. And this is the load, corresponding load. And when we release that, so we have an elastic, release. Okay, so we have an elastic release. So here we can say, so this is the elastic release. All right, so here, so suppose here it was this, or this is the maximum displacement. Okay, then it was released, so this is the elastic settlement and this is the plastic deformation. Okay, so here we have, this is the total deformation, so this part is the plastic deformation and the rest is the elastic deformation. So what we do in cyclic plate load test, so we take out this elastic displacements, or elastic settlements for the corresponding load, and we plot it. So this is the elastic settlement in mm, and this is the load per unit area in ton per meter square. So basically there is a plate and that plate is loaded. So when there is load, so there is settlement, and then load is released, so it is released. So we have a, the load, the plate first settles, then it goes up a little bit. Okay, so what amount it goes up, so that amount is measured and we plot it against the load and we obtain Cu. So here in this particular test, it was given that for P equal to 15 ton per meter square. Okay, so Cu is equal to, it was given 7.6 kg per centimeter cube. Okay, so if I consider here, so it is 15 ton per meter square, so 15 ton per meter square divided by 2 mm. So 15 ton is 15,000 kg. Okay, so kg, and this is meter square is 100 into 100 centimeter square. Okay, and 2 mm is 0.2 mm, 2 centimeter. Okay, so 1, 2, 3, 1 2 3. Okay, so divided by, so 1.5 by 0.2 kg per centimeter cube. So we have how much? 1.5 divided by 0.2. So we come to a value of 7.5 kg per centimeter cube. So I mean, some amount is there, so we can see it is not exactly 2, so I think they have considered that amount as well. It is not exactly 2, so they have calculated it to be 7.6 kg per centimeter cube. So that is Cu. Okay, so that is basically the slope of this. Now the thing is that this Cu that has been calculated, it is corresponding to 15 ton per meter square. Okay, and we have to find out what is Cu corresponding to 10 ton per meter square, 1 kg per centimeter square, that is. Alright, so that we can use that in our calculation. Just look into the this whatever material I have given you, so it will be easier to follow in the next class, because this part, especially this determining the soil parameters, is very important part. Okay, so obviously the next part is very easy, because the next part is determining the CG of the systems. So we have this one block, we have this second block, and we have this block foundation, so we have to find out what is the CG. Okay, so very easy, just a geometrical problem. Apart from that, we have to find out what is the moment. Of course, there is another point which we need to look into thoroughly. All right, so that is the eccentricity and the application of the load during the operation of the machine. Cu is equal to 7.6 kg per centimeter square for P of 15 ton per meter square. Okay, and we have to find out what is the elastic settlement as well at that point. Okay, so we have to find out what is the elastic strain. So how to do that? So obviously, how to find out Cu corresponding from this load settlement curve, we have already discussed. So what we have to do is, so here we have to find out what is the load increment at the center of the plate. Okay, so we have this plate given for the plate load test, cyclic plate load test, and the dimension of the plate was given as 60 centimeter by 60 centimeter. So what is done is, it is divided into 4 parts. Okay, and this part is considered. So this part, if we consider, it is 0.3, 0.3 by 0.3, and obviously now we have to find out what is the stress at the center. All right, so that is at 0.3, so 0.3 depth, at the depth of 0.3, because we will consider this entire length. So we will consider this length, that is 60 centimeter, for analyzing the strain. Okay, for analyzing the strain. So we have to find out what is the mean stress here at the middle of this. So we have this factors given by Taylor 1948. All right, so influence factors given by Taylor. So we have M is 1, definitely B by Z, so Z is 0.3 and B is also 0.3, so we have M is equal to 1. Similarly, L by Z we will have 0.3 by 0.3 again we will have 1. So M is equal to 1, N is equal to 1. So we have to find out what is the influence factor Iz. Okay, so influence factor Iz we obtain from here. So M is equal to 1. So M is equal to 1 and N is equal to 1. Okay, so this one. So 0.18. Okay, and ultimately we obtain what is the influence factor. So it is 0.18. So this is the influence factor here. Okay, so the influence factor which was obtained here is 0.177. So obviously you will know that when there is a load given on a plate, so the load is distributed in the soil profile in this manner. Alright, so if this is QS, so we will have stress isobars. Okay, so here you see it is 0.005 of QS. So this is 0.005 of QS. So this is 0.01 of QS. So similarly as we go on, so ultimately this will be QS. Alright, so QS is only here. And as we go at the depth, as the depth increases, so we will have decrement in the stresses in the soil. Alright, so the stress will be distributed. So based on that, so Taylor has given the factors, so influence values corresponding to depth at a depth Z. At a depth Z, what is the increase in the vertical stress delta Z? Okay, what is the increase in the vertical stress delta Z? So here, what we did is, what they have done is, so the plate load test was done for a plate of 60 centimeter by 60 centimeter into 4. So what is the increment at this point? So due to this loading only. So at this point that is. Okay, so this is 0.3. So we have to consider 0.6 depth to find out the strain. So strain will be 2 mm by 60 centimeter that is. Okay, so that will be the strain here at this point, at the center point, because there is a settlement of 2 mm. So there is a settlement of 2 mm, elastic settlement of 2 mm. So elastic strain at that point is this length divided by, so that is an approximate, alright, so approximate elastic settlement corresponding to the length and width of the foundation. So if we consider only 1/4 of the plate, so this is 0.3, this is 0.3 and this is 0.3. So it becomes easy to find out what is the delta sigma Z or increment in the stress at that point. Alright, so I hope you remember this. So this is obviously again for analysis of elastic settlement when you study the foundation system. Obviously this is not in our course, but just to know how to find out the coefficient of uniform elastic compression from the cyclic plate load test. So for various loading conditions, so I am just repeating this. So here now M is B by Z, so Z is 0.3 we have defined. So B is also 0.3 and Z is 0.3. Similarly N is also 0.3 and Z is also 0.3. So ultimately M is equal to 1 and N is equal to 1. So for that we have to obtain IZ. Okay, so N is equal to 1 and where is M is equal to 1? So 1.6, 1.4, 1. So this is, so it is 0.18, it is here from the graph we can obtain 0.18. In the example given in the book, it is given IZ is equal to 0.177. Okay, so I mean close enough, it is almost close enough. So we have now unit weight of the soil is given as to be 1.8 ton per meter cube. So that is unit weight. So unit weight into the depth, so that is already sigma z. So sigma z is equal to 1.8 into 0.3. What is delta sigma? Delta sigma z is equal to, so we have 15 ton per meter square on the plate, the influence factor. So that is Iz. So that is 0.18. Okay, 0.18 or 177 as the book gives, into, so this is 1/4. So this is 1/4. Obviously for 4 consecutive parts here, so we will have 4 times of this stress. So into 4. Okay, so total stress at that point, sigma z is equal to 1.8 into 0.3 plus 15 into 0.177 or 1.8 into 4. So that is the total stress. Okay, we can say sigma z initial. So this is the initial. So the total stress is 1.8 into 0.3 plus 15 into 0.18 into 4. We have total stress is equal to, total stress at this point, sigma z is equal to, we have 11.16 tons per meter square. So we have to obtain, so here Cu is obtained for an area of 60 centimeter by 60 centimeter. Okay, so we have to obtain for an area of 10 meter square. Area, so that is the area difference. Stress differences, we have obtained the Cu for 15 ton per meter square. Okay, and we have to obtain Cu for, basically we have to obtain it for area of 10 meter square and load corresponding to 10 ton per meter square. I hope you remember this equation. So we have, if we have Cu2 and Cu1, okay, so two values of coefficient of uniform compression. So we have E2 by E1 is equal to G2 by G1 is equal to sigma 2 average, that is, alright, so average, that is sigma 2. So this is effective mean confinement obviously, and sigma 1 into area 1 by area 2. Okay, so we will use this expression. So Cu2 by Cu1 is equal to sigma 2 by sigma 1 into A1 by A2 is obviously for 10 tons, we require it for 10 tons, we require sigma 2. So sigma U2 and sigma U1. U1 is already we have obtained 7.6 kg per centimeter cube. Okay, and that divided by, we have that obtained for 11.16 ton per meter square. Alright, so at a depth of 0.3 meter, that is at a depth of 0.3 meter. Okay, so that is one. Then about the area. Okay, area we have obtained is, so A1 is 0.36. So this is 0.6 into 0.6, so 0.36. Okay, so we have 0.36 area, and the area that we require, A2, is 10 meter square. Okay, so ultimately we will have Cu2 is equal to Cu1 into this calculation, whatever you have. So Cu2 is equal to, we will get 1.36 kg per centimeter square, centimeter cube, sorry, centimeter cube. Okay, so this is Cu2. I will again discuss this in the next class because this is a little bit complicated, but it is important actually. Okay, so this is the important part of the numerical problem. Apart from that, this is easy. Okay, so we will continue this in the next class. We will stop here.